Hello, I'm Lindsey Leach, and in this series of 2 videos we are going to be talking about 2 common uses of the chi-squared test. In this video, part 1, I will show you how to use the chi-squared goodness of fit test. You can use this test to see whether your data for a single categorical variable follows a hypothesized distribution. In part 2, I will show you the chi-squared test for independence, or the contingency chi-squared test. You can use this test to see whether there's a relationship between 2 categorical variables. Imagine I breed Labradors and you are coming to see me to choose yourself a new member of the family, a beautiful Labrador pup. You find that some of the pups are black, some are chocolate and some are yellow. They're all adorable, but still, it's a tough decision. So what's the relevance of all this to the chi-squared test? Well, this is an example of a common situation where the variable of interest, in this case Labrador coat colour, is categorical. It falls into one of several possible groups. Now I tell you that I have 80 pups that I have raised by breeding together my best black dogs. Most of them are black, but there are chocolate and yellow pups too. I have a theory that coat colour is controlled by just 2 genes. If this is true, I would expect to see a ratio of 9 black dogs to every 3 chocolate dogs to every 4 yellow dogs. Don't worry if you don't know anything about genetics, just take my word for it that if you know enough about the genes, you can work out what proportion of the pups are expected to be black, chocolate or yellow. If my theory is right, the different coloured pups in my collection should occur in the predicted ratio. In other words, my null hypothesis is that there's no difference between the expected and observed frequencies of colours. So how do I test this hypothesis? I will start by laying out the data in a table like this. Each pup colour is shown in a different column. In the first row, I have set out what I expect to see if my null hypothesis is true. If there were 16 pups, I would expect to see 9 black, 3 chocolate and 4 yellow. Scaling this up, then if there are 80 pups, then I expect 45 black, 15 chocolate and 20 yellow. In the second row, I have set out how many pups of each colour I have observed. You can see I've observed more black pups than I expected. The question is whether this difference is small enough that I can ignore it and say it was probably down to chance, or is this difference so big that it can be deemed statistically significant. We first assess the difference between the observed values and the expected values in a particular way. For each pup colour, I calculate the square of the difference between the expected and observed values, and then scale that number by the expected value. For example, for black pups, we get 225 divided by 45, which is equal to 5. So, if I want to know how much difference there is between observed and expected across my whole data set, then I can add the 3 numbers up to give 5 plus 1 2/3 plus 5, which is equal to 11 2/3. And this is my chi-squared value. So what we've done there is simply to apply the chi-squared formula, which is usually written out like this. Now, to reach a conclusion, I need to know if my chi-squared value of 11 2/3 is so large that it's unlikely to have arisen by chance. To know that, I first need to know the degrees of freedom, which is calculated as the number of categories minus 1. In this case, 3 minus 1 is equal to 2. Then I can go to the probability table for the chi-squared distribution, which lists out the chi-squared values, called critical values, for different probability levels shown in the columns and for various degrees of freedom shown in the rows here. For example, at a probability level of 0.05, the critical value is equal to 5.99, while at a probability value of 0.01, the critical value is equal to 9.21. Then I can use the simple rule that if my chi-squared value is greater than the critical value shown in the table, then I can reject the null hypothesis. Otherwise, I must accept my null hypothesis. My value of 11 2/3 is greater than the value in the table of 9.21. So there's a less than 1% chance that I would see the value of 11 2/3 or higher if my null hypothesis is true. Or I could have used my computer to work out an exact p-value from the chi-squared value, which comes out as p equals 0.0029. In other words, my hypothesis of a 9:3:4 ratio does not give a good fit to the data. So my theory about the genetics must be wrong, and it's back to the drawing board for me.